variability-based design methods of oil foundations on the static and seismic loads. His research interests include offshore wind energy foundation, soil pressure interaction, dynamics of soil and foundation, railway geotechnics, and geotechnical earthquake engineering. He started his teaching career in the year 2009 as assistant professor at the IIT Bhubaneswar. Now he is holding the position of professor in the same institute. Along with the teaching experience, he has a industrial experience. He worked as an assistant engineer at Simplex Infrastructure from 2000 to 2003 and as a geotechnical engineer at WS Atkins Bangalore from 2008 to 2009. He has published 76 research articles in various national and international journals. He has a life member of Indian Geotechnical Society, life member of Institute of Engineers, member of International Society of Soil Mechanics and Geotechnical Engineering. He is a reviewer of NPTEL web-based course on structural reliability. He is a member of Board of Studies in Civil Engineering, ITEL. He is a reviewer of journals, Journal of Geotechnical and Geoenvironmental Engineering, International Journal of Geomechanics, Soil Dynamics and Earthquake Engineering, Geotechnical Testing Journal, Ocean Engineering, and Journal of Structural Engineering and Geology. He has an international collaboration subject. And he is a visiting faculty at Department of Civil Engineering, Lansdowne School of Engineering, York University, Canada, in 2014. He is an excellent paper award issued from the International Association of Computer Methods and Advances in Geomechanics for the paper Failure Mechanism of Soil Foundation in Liquefied Soils. And also, he is actively involved in the major consultancy works. I sincerely thank the conveners of this faculty development program for giving me this opportunity to interview the eminent personality, Sumanta Haldar sir. With a brief introduction, I would like to invite Sumanta Haldar sir to start the session with his presentation.
It's a very elaborative description about thank you everyone. Thank you IITL for inviting me for this particular lecture and this technical development program. Thank you, Soujanya. I especially thankful to Soujanya. She only invited me. So the first session basically I generally work on with offshore wind energy converter, University offshore wind energy foundation. So since the faculty development program is on sustainable and resilient civil infrastructure, so I thought of giving some background of this particular topic because I have been working since last 12 years in this particular area. And although my research area was by foundation, so I thought this offshore geotechnics and offshore wind energy converter is a very interesting area and very challenging area. So to begin with, basically I will tell you about the offshore because I have been given a lot of time to present, so I have prepared many slides, but I don't know how much you can cover. And what is the audience like? What is your background? Like, are you all faculty or student? Mix of faculty students. Students MTech level, BTech students are also there. BTech final year. Okay, so that means all of you have gone through the Soil Mechanics Foundation Engineering courses, some of the courses related to structural engineering also. Because this particular presentation not only focused with the geotechnical engineering, to some extent structural engineering also. So it's a mix-up thing. So first of all, this particular program is designed for sustainable and resilient design. So first of all, what is sustainability? So all of you are talking about this buzzword sustainability. So many are doing many things related to sustainability. Now, what is sustainability? To begin with the sustainability topic, the sustainability is basically a harmonious coexistence of the human society, environment, and economy. It's a very broad terminology. So if you look at this particular Venn diagram, so the social, economic, and environment, when all three are combined, like we have a common set. So we all three means sustainability. So although the United Nations has formulated one definition of sustainability which is more general in nature, but the real sustainability in engineering is to some extent is different. So sustainability and geotechnology, if you look at the construction industry nowadays, the 40% of the global energy consumption is mostly related to this particular area, the construction industry. So they mostly replace the 2/5 of the sand resources, gravel, stone reserves every year. So it is a huge quantity. And if you look at the sustainability point of view, so the meaning of sustainability means we have to utilize the resources like for to meet our demand, to meet the basically the expectation of various level. But at certain level, so we need to always think about the future generation. So the future generation should also meet that demand, right? So that is the meaning of the sustainability. Sustainability. So we should utilize the material in such a manner, should not overuse, should consider all those aspects. So that is what the initial couple of slides I have collected some of the things related to sustainability and geotechnology. What is the real meaning of that? Then I will move towards the sustainable design of various foundations, sustainable energy and other things. So basically the problems mostly because of this utilization of this material results in the climate change unification, as we all aware of this, desertification, the deforestation, soil erosion, land and water pollution. So all are basically related to the global climate change and other scenarios. So we need to really think about it, and we need to utilize the resources in such a manner that we should use some kind of like usage of those materials so that we can recycle all those materials. So nowadays a lot of recycled materials are being used, like waste material is being used. So these are all comes under sustainable development. So therefore the geotechnical projects, so any geotechnical projects which basically involves many the societal, environmental, economic issues, and so we need to improve the sustainability of geotechnical processes, which are very much important to achieve the overall sustainable development. So that is the major objective of any sustainable process. So any technology, any sustainable technology which we are talking about, the sustainable system is basically it's nothing but the ability to survive and retain its functionality. Right? So over the time. So over the time we should use that particular material so that it will serve the purpose as well as it will be sustainable as well, so it can be recycled and be engineered. So any engineering system should be these are the four important terminologies like efficient, reliable, resilient, and adaptive. Now what are they? So to start with the efficiency, efficiency means the efficiency in terms of the efficient utilization of the material, like sustainable material, like use of waste material and other material that we are basically dealing with, which can be used for geotechnical engineering as well as the structural engineering, material science. So all those basically engineering disciplines, they use this material. So you need to efficiently utilize this material, keeping in mind the cost part as well as the environmental impacts. So basically life cycle cost analysis we do for various type of projects. So it basically gives you the amount of the carbon dioxide emission. So basically that basically related to the amount of carbon footprint, so that we are going to utilize. So that really is a concept. So that's why the efficient design, it involves all those components. It also leads to the environmental impacts. As well as the reliability. Now what is reliability? Reliability ensures an efficient design, keeping in mind the criteria for the design, like the any predictable failure state. It should be sufficient from the predictable failure state. So that means when you are designing something like a structure or geotechnical structure or any structure, you need to know the its failure criteria. So keeping in mind that particular failure criteria, you need to so that you need to reliably design. So basically, there's another way of designing the system, like the reliability of that particular system that can be ensured. But like a lot of like development have been done on this particular topic. I have also worked in reliability concept of design. So those are basically the probabilistic way of designing methods in reliability term. And the resilient. Resilient is also important like terminology nowadays, sustainability and resilience. It's basically the ability to return its original functionality. So that means when a structure is subjected to certain storm surge or cyclone or any extreme event, so deterioration of the structure is expected. Now, after deterioration, whether the structure will be usable or not, or what effort you have to make it usable. So that means you have to go back to its original state. So that is for the resilient design. So that means deterioration again, further restoration again, there may be subject to another type of loading. So it's a continuous process. So the resilient structure, the design of resilient structure is very important nowadays. So this is what that is defined here. And adaptiveness, the responsive to gradual and natural changes within itself and its environment. And so basically you can have the flexibility of modification of certain design methods. So that is called adaptive design. So it depends on the needs of the projects, right? So that's why adaptability is very much important. So all these concepts are relevant to the sustainability of the system. So next slide it will show you that the objectives of the sustainability. So it's basically very important diagram. Of course, this diagram I have collected from literature. So it is called 4 E's. 4 E's. So you can see the 4 E's. It's equity, environment, economy, and engineering. So these are all basically the 4 E's. The sustainability, when we are talking about the sustainability of engineering or of any structure, we need to satisfy these 4 E's. So these 4 E's are very important. So basically the we should not compromise the functionality of the any system. So if you look at this diagram, this is a very interesting diagram. So all are interrelated. So the environment, engineering, so all are interrelated. Equity, economy, and all interrelationships are having some conflicts, like conflicts. So if you want to satisfy something, other may be compromised. So without compromising much, so you can have certain kind of like adaptiveness in this system. So this is a very important diagram to solve the sustainability in engineering. So in this particular diagram, it shows that when you are referring to some sustainable development or sustainable engineering, you need to satisfy all these points. Okay? So that is what the objective is. Now these are the sustainability objectives to be incorporated. So these are all basically certain things like how do you implement the sustainability in a particular project. So all those points are listed here. So first point is basically it's basically involving all stakeholders. So when you are designing a structure or working in a particular project, you need to always see with all the stakeholders to meet the demand, to meet the expectation of all the stakeholders. So that is what called sustainability. Like it doesn't mean that you should not include someone who is also part of that project. So basically those are basically important parts. So that involving all stakeholders at the planning stage. So which is very much missing in all projects, but we have been seeing that. So many projects, when the project is under developing stage, many things have not been considered. But when during the execution stage, it is seen that some problems are occurring. So and that essentially happens because of the improper planning at the initial stage. And many state government projects are like that. So that we have been helping many state government agencies, and where we found a lot of problems occurring during the execution stage where you cannot go back to its original point. So you cannot change it. So that means it is not an adaptive. Right? So to make it more adaptive, you have to involve all the stakeholders at the beginning. This is an important part of the sustainability. And reliable and resilient design, that is also important. Another is the minimal use of resources. Minimal use of resources and energy, planning, design, construction. So you have to use certain materials like locally available material, or if the material is it's a natural material like sand and other material. So we need to minimize the use of those materials. So you can use utilization of waste material in place of natural material. That is more called sustainable. And so basically the existing geotechnical facilities, you have to use it just as we mentioned that. So utilization of waste materials and other things to minimize the waste. And the last point is a multi-criteria based sustainability assessment framework. So how do you assess the sustainability in a project? So this is also very important flow chart. You can see that in geotechnical design, you need to do cost benefit analysis, then life cycle cost assessment, then life cycle assessment. Then it's a very interesting method of to assess the sustainability of the project. To some extent, it's called the sustainability index. The sustainability index can be evaluated for a particular project based on this flowchart. So you can do the life cycle assessment, you can do the cost benefit analysis, and you can do some scoring, like resource efficiency score, environmental impact score, socio-economic impact score. All those scores basically you can collect it and you can make a sustainability index, and based on that you can score a particular project, whether how much it is sustainable. Right? So sustainability scale. So this is a very new area of doing research in this particular domain for any project. So what we have been dealing with, like foundation construction or any kind of project. So we can do this. So to measure the sustainability of a particular project. So we need to. It is expected that sustainability index to be high as much as possible. Okay. So coming to the, see, these are all sustainability to some extent that I have covered. So basically, it's a very preliminary discussion. So sustainability, many things can be done in terms of engineering sense. So basically, based on the sustainable development, so nowadays you know that India is going towards more renewable energy. So that is a global demand, right? So day by day, the global increase in energy demand is happening in India also. So you can see that I will show you certain statistics in terms of Indian context. What are the energy demand nowadays and how far we have gone, and then I will discuss about the different techniques to meet those demands, and to some extent the structural and geotechnical point of view. So what are the important challenges to meet that particular criteria, and what are the different type of structures like which we can think of in future, right? So to meet that demand. So coming to the global primary energy consumption, you can see that India and China, all they are competing. So basically, if you see the in terms of United States and other countries, European countries, energy demand is very substantial. Like see, you can see that in India, it's an increase in Indian energy consumption. Basically, from 11%, it increased by 11%. So from 5% to 11%. Is more than double. So in 2016 the demand was 5%, now by 2040 it will increase by almost double. And to meet the demand, of course the renewable energy may not be the only solution. So many other solutions we need to think of, like India is going for, of course the thermal power and other sectors are major source of energy development, but many like hydro projects are there which are also renewable energy. You can see that the solar energy India government is now promoting more about the solar energy. So, but wind energy is also very much challenging in India. So we can have enough capacity of wind. So basically, we have a lot of wind resources in India, Indian offshore. Of course, some onshore wind energy are available in Andhra Pradesh and Rajasthan, but offshore wind energy is also very much we have a lot of resources. So which can be utilized in future, so to meet that demand. So if you see the projected primary energy consumption of India, so in the last say 1996 to 2016, if you look at the scenario, the renewables are almost 35%, and remaining others are like coal, gas, oil, hydropower, and nuclear. So we have very limited number of nuclear power plants in India. So only 7% is the contribution of all the energy. Mostly the coal and gas, right? So coal energy, and the oil and the hydropower is also very small, because in certain parts of the country it is very good in generating the hydro energy, but not other parts. So this particular energy consumption will produce greenhouse gas emission, right? So that basically results in climate change. But the scenario is going to change next couple of years. Of course, it is showing these renewables, but of course the projected renewable energy rate is quite promising in India. You can see that. So the solar energy is substantial. So day by day it is increasing. So you can see that in 2021-22 it has increased 10% from 2.7%. So the this is the target share of renewable energy in India for consumption. So mostly it is basically non-solar. But if you look at the solar energy, so it is improving. So now India government is giving lot of schemes to implement the solar energy. And this is state-wise distribution of renewable potential in India in megawatt. You can see that. So the mostly the wind power in Andhra Pradesh is quite promising. Gujarat is promising. Karnataka, then Andaman Nicobar Island, Lakshadweep and Puducherry, all the coastal belts you can see. Even in Odisha also it is not so high, but still we have certain like promising data. Like so, we have a lot of potential like in these places. And of course, the most of the percentage you can see is occupied by the solar energy because there is a government is giving a lot of stress on this particular energy. So that's why a lot of development happened in solar energy consumption. So this is about the installed capacity. The installed capacity of the power stations in India in terms of megawatt. You can see that in northern part and different parts of the India. So what is the scenario? Like you can see the most of the cases thermal energy is the more energy. The installed power is mostly thermal, not the renewable. Renewable energy mostly I can see that most renewable energy power stations in the southern part, and then to some extent northern part and western part of the world and islands. So the coming to the solar energy, the solar energy is a very promising. But what is the role of solar energy? Like what is the role of civil engineers in solar energy? So can anyone tell what is the role of solar energy? Do you have any role? Like civil engineers, geotechnical structural engineers. Anyone?
Maybe foundation.
Foundation of what kind of solar system? So have you seen like solar plant? Any one of you have seen any solar plant? So now a lot of solar energy development is coming in. Right? So basically the role of civil engineers, it comes in the structural as well as geotechnical. If it is a rooftop solar, it is basically mostly the structural engineers that has a lot of role in the design of that structure, especially in cyclonic areas like on the Odisha, this belt. Right? So like a lot of solar installation happened in our campus also. So during last cyclone, it's all gone. Okay, so it's basically you have to design such a system so that it can survive. Right? The solar system is very flexible system. It's very it's very what you can say. So it's a slender structure, right? So you need to design it carefully. So the criteria of the design. So any deformation in the solar system is limiting deformation is very small. Otherwise, there is a possibility of crack in the solar panel. Right? So all those things you need to consider. So if you see the National Solar Mission by Ministry of New and Renewable Energy, so MNRE is a sector of the power sector like is developed by the government. MNRE they are promoting this particular sector like all wind energy and solar energy and other renewables. Right? So in 2008 and 2009 it has reached about 6 megawatt, but it is currently India is the 5th highest solar installed capacity worldwide. You can see that. So the Made in India initiative, which promotes the domestic manufacturing of this particular structure, a lot of support is given by the government to install the solar plants. So if you see the typical solar structure, so these are all basically the ground-mounted solar panels, which we are thinking of this, like where the barren land available, so where we can install these kind of solar systems. So these are low-mounted solar panel system, and these are the the elevated ground-mounted system. And it has a lot of different types of structures, so depending upon the condition, site condition. So if you see those structures, these are all single pole structures. So one single pole and a inclined frame is attached to the solar panel. And this is a low mounted structure and it is close to the ground and it is elevated. So definitely this kind of structures are more sensitive. Right? So if the wind forces comes into this particular system, there is a possibility of large deformation. And large deformation means there is a possibility of the cracking of the solar panel. Correct. So it's called the serviceability limit criteria. So serviceability limit criteria is very stringent in this case. And especially the foundation engineers are looking for the foundation system for such kind of systems. So these are all typical foundations of the solar ground mounted solar panels. You can see that the drill pier, backfill precast pier. So all these are basically cast in place foundations. And mostly, sometimes we go for driven piles. Screw piles is the new technique of installing the solar structures to support the solar structures. In fact, we have also done some of the studies on the screw pile, or it's called helical piles, which are very important system. So the screw piles nowadays is becoming more popular for solar foundations, solar structures. It has I'll show you. So the typical helical pile and screw pile. So this is a typical helical pile of standard dimensions. This particular pile, you can see the three helix. The three helix are present at certain intervals. Sometimes we go for single helix also. So this is a single helix pile. And sometimes we go for two helix or three helix, multiple helix piles. Helical foundations, the foundations made up of steel. So inside the core is basically a steel member, a steel hollow tube, hollow pipe, and the plate, the helical plate is attached. So it has certain pitch, like it is inclined, it is not a straight, it is not a flat plate. It is little bit pitched. So that means it is some inclination is there. So the advantage of this type of foundation is it can be installed very easily. So how do you install it? You have to apply some torque. So by application of torque, you can install like augering method of soil sample collection. Collection of soil sample normally use that kind of sampler, like auger sampling and other things. But this particular pile is it can be installed very quickly. Like for any solar project, the time frame is very important. So if you discuss with any solar installation company, they always look for quick installation of the solar. They want to finish up the job very quickly and they want to disperse it. So for quicker installation, this particular foundation is very crucial. So you can complete the installation of the pipes within no time, and you can remove it also. Just applying the torque. So the design of such systems is very important. So we have been also doing certain studies on the helical pipes in our laboratories. So the helical pipe, so basically most of the solar panels, ground mounted solar panels are subjected to wind loads. Right? So and in case of seismically active areas, the lateral loading is important. So helical for the solar foundation, mostly the wind load is governed. So when the wind comes, wind thrust acts on the solar panel. So you can have two different type of loadings. The vertical loading mostly comes from the superstructure, like the gateway. And when the wind hits at basically the solar panels are not flat, it's basically inclined. So when the wind hits the structure, it has two components, vertical component as well as the horizontal. So all these foundations are subjected to multiple loadings, like combined loading. Combined loading in the sense the vertical loading as well as the horizontal. So the horizontal capacity of this type of structure is very repeatedly assessed. So basically the horizontal capacity, mostly the helical piles are good in tension because of the helical plates. Right? So, but the lateral capacity of the helical pile is also challenging. And what would be the combined capacity? So like in presence of vertical load, what would be the lateral capacity of the pile and as well as the uplift capacity of the pile? So these are all important topics of research. And many studies have been done. We have also carried out certain studies on how to improve the lateral capacity. The lateral capacity is governed and sometimes the uplift capacity and lateral capacity. These two are the guiding factors to design such kind of structure. So coming to the wind energy, so the wind energy, you can see the picture, the current scenario, like the installed capacity of the wind, mostly these are all onshore winds. So these are all onshore winds. Onshore winds means on land, inland, not in sea, not in offshore. So these are all inland capacities like onshore wind turbine installations. Of course, the solar installation is quite high as compared to wind. But India has a very long coastline, as you know, around 7,500 kilometers long coastline. And in various places, we have a lot of potential. MNRE has conducted certain studies, inquires certain government agencies, they have studied the Indian offshore and they found that a lot of capacity, right? A lot of wind resources are present. So we can generate a lot of wind capacity, wind based energy. So if you see the global status, it is basically it is called energy gap by 2050. So these are all offshore winds basically. It's an objective of it's a global objective. So by 2050 we should maintain a 1.5 degree centigrade pathway. It indicates the global warming rate should not exceed 1.5 degree centigrade by 2050. So that is the target. Now to achieve this target, this is the expected capacity that needs to be installed worldwide, not in India, it's worldwide. So the current installed capacity is 35 gigawatt, but we have to increase by 8.5 times of that capacity by 2050. So it's a very important challenge to make that pathway. So it is basically you can see that the government of India they announced in 2015 the offshore wind energy policy in 2015, and it is available online also. MNRE they initially issued a draft tender 4 gigawatt wind installation in 2 locations, 2 strategic locations at the coast, near the coast. The sea is very turbulent, so you can see that. In the coastal area, the sea is turbulent. So the waves can apply multiple loadings, like the complex loading, random loading. But at deep sea, it is quite like comfortable. Like the sea is very calm. But the challenge is the stability of the structures. So I will show a couple of things there, like the floating structure as well as bottom peak structures. So evaluation of wind turbine capacity, I will show you certain like structures, and you can imagine how big is the structure. Like these are all basically the installed wind turbine and across the world. Now in 2004, you can see the installed capacity was less than 5 megawatt. So one wind turbine can produce 5 megawatt of energy. Okay, so even initially when it started, several wind turbine manufacturers they have produced certain wind turbines which can generate less than 1 megawatt, like 500 kilowatt energy. But in 2004, you can see these are basically in UK. So less than 5 megawatt was installed. But by 2022, you can see it has increased to 15 megawatt. So that means by now around one wind turbine can produce 15 megawatt. So and it can be bigger. China has developed 20 megawatt. One wind turbine can produce that much of power. The future wind turbine you can see it can generate more than 20 megawatt. Now why it is developing? Why the wind turbines are becoming more, producing more large and it can produce the capacity more wind energy? The reason is the installation of those structures is very challenging in offshore wind, and it's very expensive. It's very expensive. So it requires millions of dollars. So just for hiring a barge, for the installation of the structures in one day, delay means few crores of money to be wasted. So an offshore environment is not like onshore environment. It is very uncertain. Anytime the sea atmosphere, it depends on the sea atmosphere, sea climate. If the climate is not favorable, you cannot do installation because during the installation process, if something happened, again that leads to huge amount of expenditure. Correct it. So because see at the offshore bottom, you cannot see the soil. So that's why offshore installation is always challenging and difficult. And this is about the install capacity around the world. You can see the India, as already I have mentioned, so about 194 gigawatt of potential in Gujarat, Tamil Nadu, and other. In Gujarat, Tamil Nadu itself, it can produce 70 gigawatt of potential of. It has the potential of offshore wind power. And this is the energy enough to power more than 50 million homes. So basically. So those are basically the future trends. So and now I think the wind energy, the first offshore wind turbine is going to come in Gujarat very soon. And by 2070, basically India will meet 50% of its energy requirement from the renewable energy sources. That is the target by 2027. So and go by net zero. By net zero means all are basically renewables by 2070. So that is the target. So the options are open. Like we need to go for offshore wind. Solar energy has some limitations, as you know. You cannot produce power all the season because of the availability of the sunlight, and maintenance is also another issue. So this is a typical offshore wind farm. You can see it is called offshore wind array of wind farms. So in an array, it's a lot of land. It's given to some farm who can develop that. And after the development of that particular farm, they will sell the energy to the government. So basically, government will sell. So basically, it's a like a PPP mode. They operate these particular farms in other countries. Like this is a typical offshore wind farm. So you can see these are called the array of turbines. It can have more than say 100 number of wind turbines in an array, and it can produce so entire array. It can produce few gigawatts of energy. So each wind turbine can produce 5 megawatt to say 15 megawatts. Nowadays we are installing 15 megawatt or more. One wind turbine can produce 15 megawatt energy. So it is quite huge. The typical wind turbine, I will just play a video here. You see that. I think sound is come. Sound is from there. So this is the typical wind turbine. Sound is not there.
Speaker box. Speaker box. Speaker. Sound का.
So this is a typical structure. You can see this is a three-blade wind turbine. So when wind turbine rotates, you can see this particular structure. The blades are streamlined in shape. So the blade has some kind of aerofoils, like we have seen those kind of ones in India, blades, aeroplanes, aeroplane wings. These are all like nothing but the aeroplane wings. So all three wings basically, these are all aerofoils, so streamlined shape. And the aerofoil technology is very simple. So because of the pressure difference, it can develop the lift force. So if you have aerofoils and the wind is passing through the aerofoil, it can generate lift force. Right? So because of the lift force, wind turbine rotates. I think the pixel is not coming, so it's so basically it's a very complex mechanism. It's not so easy, not so simple. So we need to always, and this is called the pitch control mechanism. So it is basically it can be rotated. along its axis. And by rotating the axis, you can control the wind, you can control the lift force. You can control the lift force. You can control the wind thrust acting on the wheel. And this is called the generator. This is called hub. It's called hub. It's a hub is basically contains the rotor. This is called rotor. And this is the generator which produces the electricity because of the rotation of this structure. The rotor is called gearbox is attached. So gearbox, the role of gearbox is see the wind turbine, the rotor, it rotates at a very small speed, a low speed. Right? It is the frequency is around say 0.3 hertz, right? 0.3 hertz to 0.4 hertz, or maybe even low, 0.2 hertz. So, but to generate the electricity, you need more RPM. So this gearbox, it basically changes that RPM. So by that mechanism, by this mechanics, we can generate the more RPM. And from the gearbox, the setup transformer to amplify the energy, amplify the current. So this is called the normal wind direction. So when wind is hitting the turbine. And another control mechanism is that it's called the yaw controlling. So wind turbine can also rotate along its axis. So this is basically an anemometer which can give you the direction of the wind, and this is called the yawing mechanism. So the yaw motors, it can rotate the entire assembly along its axis. So it will be always aligned to the wind velocity. Right? So the wind velocity will always be normal to the rotor. So this is the rotor. This is the kind of mechanism they apply. So this is the under operational stage. The wind when the wind is hitting the wind turbine, the blades are having some pitch angle, some angle. But when the wind turbine is stopped, this is called the path condition. The path condition when the wind turbines are in idle condition. Idle condition when it is not producing electricity during maintenance purpose or during extreme events like cyclone, typhoon. So what happens? All the wind turbines, the angle, the blade angles will be in such a fashion, it can produce a low thrust. It can minimize the thrust. Those are the feather condition. Those are called the feather condition. So that it can produce less amount of thrust. So in any wind turbine, so we can generate the wind energy. So the available energy, the wind is X. It cannot generate more than 59% of that wind. Okay, so the upper limit of the wind is called the base limit. The base limit is you can generate only 59% of the available wind energy. So this is called the theoretical maximum efficiency. The base limit is called 59.3%. So that means it can only generate, it cannot go beyond that. Mathematically, it has been proved that. So the efficiency, the mechanical efficiency is 59.3%. So you can achieve that percent by controlling various mechanisms. Now, as a role of the structural and geotechnical engineers, if you look at the cost breakdown of the offshore wind farm, the offshore wind farms, basically the water depth plays a major role. If you look at the cost involvement, the cost of the wind energy foundations like the offshore wind farm, so foundation. The cost of the foundation increases with the increasing of depth of water. The cost of the foundation is about 20% of the overall cost of the entire structure. So per megawatt, it needs around 3 crores of investment per megawatt, more or less, approximately, and 3 crores of investment. So 5 megawatt, 5 times of that cost. So 20% of that cost involvement is there for the foundation. And it may go even up to 36% you can see that if the water depth goes beyond 40 meters or 50 meters. So the optimum design of foundation is more challenging. So you cannot utilize more and more material or heavy structure for foundation. And of course you have to design a, the correct foundation for a particular structure. So this is about the offshore India. You can see the various offshore installations. Mostly those offshore installation is mostly the oil and gas those sectors. They have installed those platforms, offshore platforms, and these are major basins. You can see Bombay High, then Krishna Godavari Delta, Hooghly Delta. So these are all important locations where the offshore oil industries are basically working, and all the platforms are deployed here. Now, why I'm showing this particular area? Because particularly the continental shelf of India, it is basically land below the sea, adjoining the coast, and where the water depth is less than 200 meters, it's called the continental shelf. In Bombay High, there is a west coast, it is around 200 kilometers, but in Madras and Visakhapatnam, it is around 30 to 40 kilometers. So up to 30 kilometers to 40 kilometers, you can get this continental shelf, but it is huge in western coast. So the all offshore installation, it depends on the type of ground present in the offshore environment, how much land is available within the continental shelf, because some are exclusive economic zones within 200 meters, and these different zones are basically identified, and in high seas these are called the deep oceans. And deep oceans, mostly we are looking for those deep water investigations and those floating structures. So all those bottom fixed structures may be deployed, may be installed in this region, continental shelf. And if you look at the soil profile at eastern and western offshore, its drastic variation is present. So in Hooghly Delta, it is mostly clay, and Mahanadi Basin also the clay sand mixture. And Krishna Godavari divided the deltaic region also, you can find the layer of clay and sand. And especially the Godavari and Krishna Delta, the soil is very problematic soil. It's a very soft soil. These are under consolidated soils, and those are very, very soft soils. So the fresh deposits are there. At Bombay High, you can see it's a mixture of the calcareous deposits. The soil are mostly mixed with the shell fragments. The shell fragments are mixed. So those are called calcareous deposits. These are calcium carbonates are mixed with the sand and clay. Those are called the calcareous deposits. Those are very typical material. The behavior of such material is extremely important. So it's very difficult soil. So we have, if you see those, so in ONGC they have all this type of soils. So we have seen those soils. Those are all very some soils are very steep, just like a concrete block in Bombay High region. But in Krishna Godavari Delta region, if you see the soils are extremely soft, very soft soils. So the construction of any kind of foundation of those soils in this particular environment is very challenging. So coming to the offshore investigation, so basically these are the different offshore investigations we do. And just keep on those things now. The foundation design issues mostly we encounter the bearing capacity, permanent deformation, cyclic displacements, foundation stiffness, pile drivability, and punch through. So all these are important. Why these are important? So if you look at those foundations, I will show you the liquefaction potential and sour erosion. These are all important things. I will show you the structure now. So these are the locations of offshore energy development in India. These are the two strategic locations identified by the government. And another location may come near Goa coast, Kerala, Maharashtra. So these are the locations. So this is the you can see those blocks. Those blocks are basically identified by the government where the installation is going to happen. And mostly the The FOE, it's an agency, it's a consortium, facilitating offshore wind energy in India. It basically done some preliminary investigation, and based on the investigation, they have basically identified certain type of foundations like monopile foundation, tripod foundation, and jacket foundations. I will show you the pictures of those type of foundations that which will be used for offshore structures. So you can see that the Virat coastline, these are the important. I have mentioned this. So the components of the wind turbine is important, as I have already mentioned. So this is a typical monopile foundations. So the offshore wind turbine is basically bottom fixed structures. So it's a single pile, a single steel tubular pile. The diameter mostly varies from 4 meter to 7 meters, sometimes even 10 meters. So you can imagine how big is that structure. So 10 meter, 8 meter dia is more than this. So it's a big structure. The thickness of the foundation, thickness of those tubular structures, mostly 50 mm, 70 mm, like that, 80 mm thick. These are the basically the substructures, which are all driven piles. And the top part, you can see that this is called the tower. This is the tower. This is a slender tower. The height is about 80 meters from the mean sea level. And the top part, it contains the blade and hub and rotor. So basically the rotor, hub and blade and the gearbox and the generator. The entire system we call it rotor nacelle assembly, RN. Call it as RN. Rotor nacelle assembly. So the mass of the entire system, it is basically concentrated at the top. So that means a slender structure is a pole and a top is having very large mass. So this is a typical structure. And the bottom, the foundation is present. So under this different type of loading, the behavior of such structure is extremely challenging to design. And this is a typical power curve for the offshore wind turbine. You can see that so the power curve indicates at different wind speed how much energy it can produce. So it's a steady wind speed. You can see the cutting wind speed and the cutout wind speed. It indicates the cutting wind speed is the wind speed where wind turbine start producing electricity. And it can reach the maximum power output. That means if it is a 5 megawatt wind turbine, it will generate 5 megawatt at rated wind speed. Rated wind speed is 14 meters per second. So rated power means the wind turbine is rated for some megawatt, like 15 megawatt. So it can produce 15 megawatt energy at that wind speed. And beyond that wind speed, the power is constant. So that's why the power curve will become constant. And at certain wind speed, wind turbine cuts the basically it is called the cutout speed. So that means beyond that speed, it will stop producing the energy. So they will be automatically disconnected. Right? So just for the safety purpose. So normally it cannot rotate a large speed. So beyond 25 meters per second, the wind turbine will shut down. It's called the shutdown condition. So the cutout speed. It's called cutout speed. And these are the typical wind turbine foundation structures. So within 20 meter depth, you can see that it's a gravity-based foundation. It's a gravity-based foundation. It's a large mass structure. It's made up of concrete or sometimes ballast with a compartment. It's a heavy load. It is put at the bottom to stabilize the structure. It's called the gravity-based structure. Then the suction cushion. Suction cushion is a large bucket kind of foundation. The internal air will be basically removed by suction mechanism. So that's why it's called the suction cushion. Monopile is a common type of foundation you mostly deal with. Tripod foundations, jacket structures are generally used for intermediate water depth. So these are four-legged jacket structure, and more than 60 meters water depth, you can find the floating structures. Those are the floating structures. So floating structures are also like different type of structures are available. So these are the future trends. Already I showed this in the previous slides. And now, why we are going bigger, that already I have mentioned. So if you see the Boeing aircraft, Boeing 747 aircraft, the length is 76 meter. Now in one wind turbine, say if the capacity is 2.3 megawatt, the diameter is about 93 meter. So that means this for the rotor diameter is 93 meter. It is more than Boeing 747 aircraft if the capacity is 2.3 megawatt. For 8 megawatt wind turbine, diameter is 164 meter. So diameter is very big. So it is some few numbers of Boeing aircrafts can be accommodated within its wingspan. So it's a very huge. So it's not a small one. Right, so and now again the 15 megawatt will have a larger dimension, maybe 200 meter, more than 200 meter. So this is a 12 megawatt wind turbine. It is basically it's a wind turbine manufacturer. They have developed a 12 megawatt wind turbine. Of course, it's the older one. So it is having 107 meter length blade. One blade length is 107 meter. So the rotor diameter is 220 meter. So it's a very huge turbine. So this is a 15 megawatt Siemens Gamesa wind turbine. Siemens Gamesa is a manufacturer. So the its height is 150 meter. The tower mass, that means the mass of the blade and the rotor, is around 860 ton. 860 ton mass is placed at the top. And it is resting on monopile. Monopile base diameter is 10 meter. This is a very big turbine which is developed by the Siemens and Gamesa. It's a US offshore wind farm is being used. So the monopile length is about 45 meter below the seabed, and water depth is 30 meter, and the tower height is around 150 meter. So it's a huge system. So offshore wind turbine structures are basically bottom fixed and floating system. So these are all a summary of different type of foundation systems. Monopile foundation, jacket structure, tripod structures, and foundation structures like pile, shallow foundations. Floating system, tension link platforms, semi-submersible, and spar buoy type of foundations are basically used. So these are all different structures, like this is a replica structure, the picture of replica structures, this is a suction cushion structure, and the top one is a jacket structure. So jacket supported by suction cushions. These are monopile foundations. This is a tripod foundation. You can see that two legs, the 3 legs are present, and these are all tied up with all the members. And these are the floating structures. The spar buoy. This is basically the concept. It's basically a hollow chamber. Mainly the buoyancy is used to stabilize the structure. The stability of the floating structure is extremely important. And all these structures are tied with the anchors, ground anchors in the sea bottom. You can see those are called the spar buoy. Spar buoy. These are all basically the cables, so they are called mooring lines. These are all mooring lines. So there is 3 cables that are called the mooring lines. So these are all cables. So through cables, it is tied to the ground anchor system, and a tying mechanism with the spar buoy. The spar submersible and the tension leg platform. Tension leg platform, it is having 3 legs or the 4 legs. These are the floaters at the top. These are the floaters, and all the legs are basically cables, and it's under tension. It's under tension. So basically, one floating system is giving upward thrust, and it is also under tension. And at the ground, it is basically anchored in the ground in those tension legs. These are typical installation of the Rapidus foundations. These are tripod foundations already I mentioned. Now, out of all type of foundations, monopile foundations are very popular. You can see out of 100% uses 75% usage of monopile worldwide, and then gravity-based structure, jacket structure, and tripod structures. So the monopile is very easy installation purpose. So that's why the monopile structure is very much popular. I'll show you one video
Brief.
related to the monopile foundation construction.
రేపు తీసుకుని
నేను ఇంట్లో ఉన్నాను మేడం రెండు పంపేది
ఎక్కడ
So those are the installation of blades. So this is about the installation. And this area of wind turbines already shown in the first slide. The connection of grids. All wind turbines are connected to each other and it will be connected with the nearest line to the grid. So any questions so far? Yes.
Sir, you have shown that the wind turbines in the sea, up to certain distance, or you can say that they are fixed to the seabed, and after in the deep seas they are floating structures. So, but in the floating structures there is a compliancy, means there is there is allowed displacement of the floating platform. So that kind of dissipates the wind energy, right? So when compared to the structures that are fixed to the ground and the floating structure, so how we gauge that even the cost of construction or installation in the deep seas for these offshore wind turbines is very high. We know that because of the complexity involved. So in terms of all these things, how sustainable it is to install a structure in the deep sea with floating platform compared to this, because we have to ultimately see the cost effectiveness and sustainability. And most of the time, the in higher wind speeds, the compliancy is allowed much further. Means the reflection or and that allows and gives more dissipation of energy. But in a fixed structure like monopile and other tripod things, since it is fixed, all the energy can be maximum energy can be transformed. But in compliant or floating platforms, it is not possible. So how can we gauge this thing and decide to fix it here and there?
So basically, see, it's a good question. So the dissipation of energy, basically the floating structures, of course, these are all basically challenging environment. The floating structures, as you are mentioning, that it will dissipate more energy, but it is not like that. The floating structure stability is assessed first.
Yes, yes.
So that's why I showed you a couple of pictures related to the floating structures. The floating structure mostly the spar buoy type of formations and
PLP.
and semi-submersible and the TLPs.
Yeah.
So basically, the major problem of the floating structure is the stability issue.
Yes.
Basically, all the structures are basically high, so that you cannot allow much deformation in that field. So mostly we can have certain tilt.
Yes.
Tilting is allowed, but the tilt also has certain limits. So those tilting and those shifting, like there is a displacement, so it can deflect. Normally the wind turbine, if you see the monopile structure also, at the top the deflection may be 1 meter also, even more than 1 meter. But the deflection, other than deflection, the tilting is a governing condition. Because if it tilts, that those are all basically the flexible blades. So that may touch the your tower system. So that's why the code stipulates a very stringent criteria of the tilt. So we need to design, instead of deformation, we generally allow certain allowable tilt based on the allowable tilt, based on service units. And in deep ocean, the sea is relatively calm. So if you see the sea state is relatively calm than those shallow depth structures. In shallow depth, the problem is it's very near to the coast. So within 10 meter and 20 meter zone, the sea is more turbulent. So in that respect, if you see the cost involvement, that of course, definitely the wind energy cost, the initial cost is quite huge. But if you look at the long-term goal, if you see the long-term benefits. So if you do the cost-benefit analysis, the per unit cost that will reduce if we use more and more wind energy. Because if you see in India, if we start the wind energy, definitely the cost will be high. But the scenario is not same like UK and Norway and other countries, where they mostly rely on offshore wind. Like UK, they have most of the wind turbines are installed by those countries, UK, Norway, Denmark, all those countries, Germany, and other countries, they have installed a lot of wind. Energy cost is substantially reduced because use of the wind turbines. Unless you use it, start using it, initial cost will be different. So what the time, it will be drastically reduced. So that is a thing that we can discuss about this initial investment will be quite high.
Are there any successful wind turbines in deep sea? Is it a recent phenomenon or it has been going since decades?
No, it is.
The wind turbines in deep sea.
These are all basically installed wind turbines. These pictures.
No, I'm talking about deep sea installments.
Deep sea installment, floating, lot of floating wind turbines are coming in Japan as well as your China. Then Taiwan is also now recently they are mentioning in offshore wind farms. Of course, the UK has Norway, Denmark. They all have the semi-submersible type of foundations. And we have some pictures also. Floating offshore. So this is one which is installed in. The floating structures are not many, but this further development is required. Like those bottom structures are explored. So floating structures are coming out slowly. India still are looking for bottom fixed structures. Maybe after 20 years, 10, 20 years down the line, India will also
Still R&D going.
but other countries they have already done. Not many, but a few they have done. So, let me skip a couple of slides because time is limited. So let me. So any more questions?
Sir, my doubt is for acre land, how many turbines we can install?
Okay, so that is also a good question. So basically, there are some certain norms.
Okay.
Like if you install area of wind turbines, this is called the area of wind turbines. These are called wind farms. Wind farm normally the one wind turbine is installed around 5 times as average, 5 times of the road diameter. So if it is a 5 megawatt wind turbine, if the road diameter is 150 meter, so another wind turbine should be installed 5 times of 150 meter distance. So basically there should not be any interference between turbines because it's a rotating device.
and wind turbulence may act. It's called the wake effect, and all those phenomena may play in that.
Sir, what is the cost of one wind?
Cost per turbine, that's what I mentioned. Per megawatt around 3 crores, 4 crores. A lot of because see the offshore installation. If you see the offshore platforms, the offshore platform cost is also very expensive. Like ONGC, if you work with ONGC, you will come to know the cost. So basically, the per day those hiring cost of those barge, like the floating device which will be used for installation of those systems, is huge, expensive, and it depends on the sea conditions and the availability of the barge. Suppose if you are hiring a barge, maybe that particular barge is working somewhere in Norway or in Australia, so they will include the cost from Australia to this place, the transport cost. So it is not very small. So, but the development, if you see the cost benefit analysis, in the long run definitely is beneficial. So this is about the loads as a structure or technical point of view. To design such structures, load is the most important part. What are the different type of loads acts on the wind turbine? So here it's a very schematic diagram. Is basically it is presenting the different type of loading. So the 1P loading is basically it is a load when the wind turbine rotates. The three-blade wind turbine rotates at a particular speed. If you suppose the side-to-side direction. So this is the side-side direction, and normal to the rotor is called the fore-aft direction. This is called the fore-aft direction, and this is side-to-side direction. The side-to-side direction 1P load acts. It's a sinusoidal kind of loading or cyclic loading with the frequency of the rotational speed of the wind. At the same time, the wind thrust also acts on the wind turbine. Like when the blade covers the tower, and that particular moment, the thrust will act only on blade, and some part of the thrust will act on the tower. So this is called tower shadowing effect. The tower shadowing effect. And due to the tower shadowing effect, so it will happen 3 times per revolution. Because it's a 3-bladed turbine. So 3 times in per revolution, 3 times it will have a shadowing effect. So for each shadowing effect, the amplitude of the load will be reduced drastically. And then when the blade will pass the wind turbine, so immediately the force will be increased. So typical force diagram I can show you. So this is the typical loads. So there is a 1P loading, there is a side-to-side loading, there is a 3P loading, it's a kind of one-way cyclic loading. So for each reduction, it means a shadowing effect. So the frequency of that load will be 3 times of the 1 frequency. That means if the rotational speed is say 100 rpm, then the frequency of this will be 300. The 3 kilo. So that's why we call it the 3 kilo. 3 times of the 1 kilo. And this is the wave load. Wave loading is always acting on the structure. So the wave loads are also sinusoidal in nature. And the typical frequency of the 1P load already we have seen, it's a low frequency loading. The wave load is also around the frequencies of the period is around 10 seconds. The 10 second is the 0.1 hertz is the frequency of wave load. And if you compare the magnitude of the wave load is governing. Wave load is always governing. If you see the 1P load, the magnitude of the 1P load is very small compared to the wave load. The design approach is also interesting. You can see this is the spectral band of the wind turbine. So 1P, why the 1P shows a particular band? Because this wind turbine has variable speed. It will not operate at a particular or fixed speed. It will operate at a particular frequency range. So suppose the lower frequency range is 0.1 hertz and the higher frequency range is 0.2 hertz. That means it is a variable speed. Right? So that's why the band is shown as a 1P frequency band, and the 3P frequency band is a 3 times of that. So that is 0.3 hertz to suppose 0.6 hertz. So this is the frequency band and this is another frequency band. This is called the power spectrum density plot. Now the natural frequency, I hope all of you know, those who are BTech students, I don't know whether you know about the natural frequency or the fundamental frequency or not. Do you know about natural frequency? The concept, natural frequency of a system. You know? Do not know. Yes. So on vibrates, have you seen any vibration of any structure? First, if I take a scale and if I apply certain disturbance, it will vibrate, right? When say suppose in a building, you can feel vibration, isn't it? So that vibration, when it happens naturally, say suppose if I take a scale and apply certain disturbance, it will vibrate automatically, right? So that vibration, part evolutions of frequency of vibration is oscillation, right? So some oscillation, a period of oscillation. So that is the natural frequency. So why is it important? Because any external frequency, if it is matches with the frequency, resonance may have exists. Resonance means amplification of response and damaging of that, right? So that may happen here also. If the natural frequency, that means the overall system, if it vibrates naturally, if the natural frequency is some value, if it is falling within this zone, or here below the 1 pNGP and above 1 pNGP frequency, what will happen? Now, suppose there is a red color. If the natural frequency of the entire system falls within 1 pNGP, we call it as soft steeper. And if it falls below the 1 pNGP, that is somewhere here, it is called soft approach. And if it is fixed at beyond 1 pNGP, that is more than 3 pN frequency and 1 p frequency band, we call it as steep approach. So all these are mentioned here. So the natural frequency is defined as Fn. Now what is the implication of that? You can see, you can understand through this picture. If I design a system in a soft steep zone, and steep zone, you can see the difference. So what is the difference? If I design a structure on a soft zone, the structure will be very slender. The slender structure will deflect more. So there is a problem of serviceability criteria violation. What will happen to the steep structure? It's a very robust heavy structure. You see that the size of the turbine is bigger. The tower size becomes very large. So it is a robust structure. More material involvement. It's not sustainable. Consumption of material is more expensive. So optimum design is always soft steep. That means in between 1 and 2. So you will get some optimum value, optimum size of the structure. Let me skip this part. So how much time will we have? Half an hour?
Half an hour.
Shall we discuss? If you have any question in between, you can discuss.
Although we were what is the coding?
I will show you. I have a couple of slides related to proteins. So protein structure stability is not a very simple task. So I will show you what are the different stabilities. Material, these are all still basically hollow chambers. These are all basically high grade steel material. And with a coating of like a, you call it some cathodic protection, like in sea water, there is a possibility of sea growth corrosion. So to reduce the corrosion, we use anti-corrosion chemicals. So these are all very specialized method of construction or material engineering. And the blades are basically it's a fiber. The blades, turbine blades, are fiber blades. So out of entire wind turbine, everything is recyclable. You can recycle the entire structure, except the blades. Nowadays, the blades, the industries are looking for recycling of blades. So basically, the entire structure is steel material. So after, say, the wind turbines are installed for around 30 years design life. So after 30 years of design life, they will decommission. So that is basically under that part of the contract. So whoever is going to install, they have to decommission. So after completion of its design life, all the wind turbine will be uninstalled. So it will be decommissioned and it will be recycled. So only the blade part is not recycled material. So but still the research is going on how to make it more recyclable. sustainable results.
Why they use fibers of the
Fibers are basically, those blades are basically should be low weight. Low weight structure. It cannot be steel structure. Otherwise, you cannot maintain that speed. So the foundation modeling now I will just try to discuss about the different modeling aspects those who are working on modeling. Like this structure can be modeled by fixed base model. You know the IS 292 for analyzing the structure. We have also done that modeling. Like this is a typical simplified model using PY based approach. So how many of those? The springs are basically attached in the lateral direction and vertical direction. Lateral direction load, what will happen? It will give lateral resistance. And if I apply axial load, it's shaft friction. Right? So the shaft resistance will be modeled by TZ spring, that is vertical spring, and those lateral resistance will be
Are non-linear and horizontal ones are linear.
springs. Yes. So there are PY springs. You can see that PY springs. It's for just representation purpose. The difference between
The
non-linear
color was red and blue there.
actually, yeah, so incidentally it happened, but actually it is not. So just to show the difference between linear spring and non-linear spring, it is drawn in red color only, but it is nowhere related to the color of the spring. So the linear spring means P versus Y means P is the resistance, Y is the deformation. If the spring is having certain deformation, how much resistance it can develop. In case of linear spring, that resistance will be constant for all deformation. For non-linear spring, it may. So that is the difference between linear spring and non-linear spring. So these are all advanced way of modeling different type of structures. But API, say American Petroleum Institute, they have given certain standard guideline to model those PY springs. PY springs means for numerical analysis, we need to use those springs. Those are the elements. Those who are working on finite element-based analysis, they know that. So the soils can be represented as soil springs. Those springs can be linear or non-linear. So non-linear, how do you model non-linear spring? Based on American Petroleum Institute based PY laws, you can utilize those equations to implement those springs. So based on the soil parameters, mostly unconstrained and value of clay, friction angle of the soil is generally used to develop the equation for this. The equation. But these springs, the PI-based springs, although they recommend those various design codes they recommend, those springs have been developed for small diameters, like diameter up to 2 meters, like regular structure. But for offshore piles like monopiles, these are large diameters, more than 3 meter or 4 meter diameter. So those springs may not be applicable to those large diameters. Now, several studies have been done, but still, many industries they recommend this particular spring with careful use of those springs. And certain modifications have been also proposed by certain researchers to develop the PY springs, like modification of the API-based PY springs for large diameters. So those can be seen, some of the papers can be seen. And the foundation soil interaction is important. Because you know this piles, the monopiles are basically when it comes to wind turbine piles, basically experience 10 to the power 7 to 10 to the power 8 cycles of loading for the center design life, the millions of cycles of loads. It's not like earthquake loading. Earthquake loading, it happens for 10 to 12 cycles of loading. But offshore foundations are exposed to millions of cycles. Now, what will happen to the foundation system over the long term? That is also important because the monitoring of those foundations in field is extremely difficult. Because for 30 years time you cannot record the data, but still monitoring is being done. So the surrounding soil will be subjected to shearing as well as compression. So the straight softening, straight hardening behavior you may experience for loose sands or dense sand in sandy soil. For clay, the degradation of stiffness. So this is a typical representation of the soil movement interaction. And these are the typical PY curve from the attributed file. I'll just keep a couple of things here. The size elements of PY curve I don't want to discuss right now. cyclic terminal load all. So this is a typical PY Institute 2011 code. The development is done, but the equation is same. So this is a typical PY model. It's a degradation. So this is the ultimate strength of the soil, residual strength. So after degradation, soil that is called residual strength. This is called clay. Similarly, for sand, you can see for different type of number of cycles, some stiffness regression effect is modeled. Okay, so these are what done by us or the group. So importance of soil structure interaction is evaluated. Like if you use the fixed base assumption and flexible base model, what are the difference between in terms of response of the system? And this is a long-term behavior. Stiffness degradation plays major role. This is the experimental work that we have done just to show the long-term behavior of the model pi. So the model pi test we have conducted in our laboratory, and the response was basically recorded during the test. And of course, you cannot test the real structure, you have to scale down.
So what are the soil formation there?
This is clay, it's
Clay.
kaolin clay.
Okay.
This test is done using kaolin clay. It's a soft clay.
Soft.
Soft. But we have consolidated for certain marks.
Okay.
So to some extent over consolidated. And now this is a typical response we have noticed after. So we have conducted the test after 50,000 cycles, but we cannot conduct this for 1 million cycles. It's huge. So 50,000 cycles, some reduction in the frequency of the this natural frequency change may happen. You can notice what is the implication. So earlier I showed you 1T and 3T plot. In between natural frequency, if it happens, then if I design the structure, if it falls within 1T and 3T, we call it a soft strip structure. Initial frequency is at the middle of the 1T and 3T. Now due to the change in frequency, so if the modes of vibration is sway bending mode, so till you can see the natural frequency is 0.25 Hz. In that case, sway bending mode is mostly it may occur. But if it is a liquefaction condition, or if I shorten the coil, what will happen? The tilting vibration will be predominant. You can see that the natural frequency becomes very small. Vibration can be activated. That's for that may be detrimental for the design of system. So that is a major implication of the seismic design. Similarly, the vertical mode of vibration. XY vibration and on vertical vibration, right? So vertical vibration is neglected on seismic design. But in case of intermittent structures, vertical vibrations is involved. You can see this is a vertical mode of vibration. And in fact, in case of, normally the long pipes, the vertical frequency is quite large, which may not match with the seismic excitation frequency. But if we design a short pipe with liquefaction, natural frequency will be reduced to say about 0.5 Hz. Right? So that may like match with the excitation frequency of the seismic mode. So that is the implication is that mode can be activated, and there will be possible vertical vibration, amplification in the vertical vibration, and that basically gives the amplification, a very large amplification at the top. Now, one of the design criteria is at the top, at the rotor level, if the acceleration level goes beyond 0.5 g, then it will automatically shut down. The entire system will be
The
shut
vertical
down.
acceleration.
Yes. Vertical or horizontal, anything. Vertical or horizontal acceleration, it goes beyond 0.3 or something like 0.5, maybe 0.2 to 0.3 g. as per the criteria. If it goes beyond that level of acceleration at the top, it is called the emergency shutdown. So emergency shutdown will be activated. So wind turbine will be stopped. Now what is the implication of that? So if wind turbine shuts, then it will stop producing electricity. One day idle condition may lead to huge amount of loss, energy loss, right? So that is another important aspect under vertical motivation. What we have observed, there is a large amplification in the vertical vibration in the top due to this reason.
Sir, any torsional participation?
Torsional vibration may not be predominant in case of monopile foundation. It may happen in case of tripile, like three leg platforms are there, three-legged piles, three is called a tripod, or four-legged, three-legged jacket structure.
Jacket.
So this is a typical numerical model one may try. So it's basically combination of the free field motion and the near field motion, and allowing the system that we have tried and we have done some analysis. And you see the natural frequency variation under operational phase, under liquefaction phase, and the post liquefaction phase. So if the post liquefaction behavior, say when so this particularly happens, it may happen in case of Gujarat region. In certain cases, in certain regions, in Gujarat soil is liquefied ground. Like near the Kandla port and other regions, the liquefied ground soils are there. If any turbine is installed, so during the operational phase, due to the accumulation of the strain, so basically it is done for sandy soil. So due to the gradual densification of the soil, natural frequency is slightly increasing. And liquefaction phase, due to the drastic change in the stiffness, suddenly drops. Right? So the liquefaction phase, you can see the natural frequency will drop. In post liquefaction phase, due to densification, the post liquefaction, the soil will get density, and that will recover the natural frequency over the time. Right? So this is a post liquefaction. This is a very interesting behavior we have observed, considering certain laboratory based examinations.
So the post liquefaction phase, the increase in natural frequency is due to the
Due
consolidation.
to the densification and concentration. We have published one paper also, you can go through this paper. One of my videos this week. This is another interesting diagram. It is called cyclic load response diagram to determine the hazardous region. It's based on the liquefaction concept. So depending upon the moment loading and horizontal loading, if you know those loads are acting on the structure, you can identify a particular zone based on its tilting value. Which zone is more severe and moderate and less severe. So more detail can be get from these papers. So we need a lot of discussion with this. You can get these papers and see the work. And this is a typical resonance under different earthquakes. Like you see, for this particular case, no resonance happened. For this case, you can just see the comparison. You can compare these two results. So this is a typical resonating behavior. So amplification of the response acceleration happens, especially in case of data. This is just an analysis we have done using data and process structure. This is a typical application. Just skip those.